the emojis that best express your emotions at this point. Let's have a few of the emojis. Feel free to use some of the emojis. So our guest speaker for today is Abdul Yusuf. Is So Abdul Malik Kamate Yusuf is an accomplished AI machine learning engineer with strong expertise in building intelligent, data-driven systems. He currently works with the Mino Health AI Labs, where he contributes to development of AI solutions aimed at improving healthcare delivery across Africa. In addition, he works with Analogic LLC, where he helps build tech-driven solutions for clients, ranging from full stack software development to machine learning engineering. His work spans applied AI, back-end systems, and data science, with a strong focus on translating ideas into scalable real-world impact. Abdul Malik is deeply passionate about using technology to solve complex societal and industry problems. So I think will kindly join me with your reactions in welcoming Abdul Malik to give us a presentation for today.
Great, great. Thank you, Leslie. Uh, please confirm if you guys can hear me. All right, right. Great, great, great. Okay. So quickly, let me share my screen so that we take it from there. What's happening? Right. I hope my screen can be seen, right?
Yes.
All right, thank you. Which screen am I sharing? All right, thank you, Leslie, once again. So today we are here again to continue with our previous section, and hold on, I'm coming. And today we are going to learn how machine learning helps us to make better decision when we are uncertain about the outcome. All right. So, because every just like engineering decision involves some level of uncertainty. All right. So, my goal for this section today is to understand the core tools and be able to start applying them, right? So, but before we move on to today's class or today's section, for the sake of those who are joining only for today, I would like us to throw more light on what we did last week, right? So because this class is a build-up session from the last 2 weeks class, and most of the stuff that we did the last time, we are not going to do them again, though I'll be touching one or two stuffs, right? So last last week, we looked at machine learning driven predictive analysis, right? So where we looked at what actually is machine learning, where we demonstrated that machine learning is when machines learn from data and discover patterns and trend, right? And whatever outcome that comes at the end of the day is what we term as predictive analysis, right? And from there, we made mention or we looked at the workflow of machine learning, what it takes to come up with a good model. And we went through a case study, all right, in a notebook, right? So, for the sake of those who didn't come last week, because today we are not going to look into any code or something of that sort. We are going to take what we did the last time and just build upon it. All right. Yes. So let me put the notebook in the chats for the sake of those who didn't come last week. To After this section, you can go through and know what we are talking about concretely. All right. Yes. Crazy. Okay, so before we start, I would like to start with this simple question. Yes, like imagine you could drill a well for $50 million. If there's oil, you make $200 million. And if not, you lose $50 million. Should you should you drill? So basically, the answer depends on the probability of success. Right. And that's what this whole workshop is about, right? Putting numbers on uncertainty, yes, like instead of guessing, right? So most of the time, we, yes, like engineers, most of the time we guess numbers when it comes to making like analysis or coming up with risks. We sometimes guess numbers, right? So basically today we are going to see how we put numbers on, yes, like uncertainty, right? Yes, like instead of guessing. So we are like looking at what, yes, like uncertainty. We don't know, yes, like everything. And probability, we can measure what we don't know, right? And that's where machine learning comes in. And machine learning, computers can learn patterns from thousands of past examples, and at the end of the day, tell us wells with these features have 75% of success rates, right? So at the end of the day, machine learning has able to quantify or measure this uncertainty, right? So that you can be able to make decision that account for what could go wrong. All right. So as I said, today's class is a build up from last 2 weeks, what we did last week. So before we go further, I would like to ensure, yes, like everyone understand what machine learning actually is. All right, because today we are going to get maybe new people joining us today. All right. So what I want you to understand is machine learning is not a robot. I'm saying this because my first encounter, my first day like encounter with machine learning, I pictured machine learning to be a robot because my first time I heard it from Elon Musk, that was level 100 second semester, where it's like Elon Musk was trying to explain how they are using machine learning to build self-driving car, right? So from that perspective, I saw machine learning to be kind of system, to be kind of robots, right? So that was my first encounter with machine learning. So today I'm trying to yes, like highlight this so that you don't see a machine learning to be a robot, right? But yes, like it's a computer that finds patterns in historical data and use those patterns to make predictions. All right. So basically think of it as an, yes, like experience. like engineer who has worked on 500 walls, right? So they develop, yes, like intuition, right? And at the end of the day, that's what like machine learning does. But one thing about machine learning is faster, and also it comes up with numbers. All right, so that's what machine learning is. And last 2 weeks, we looked at some type of machine learning. We looked at supervised learning, where you show the computer label like examples, and we have like unsupervised learning. We don't have yes like labels, so the computer try to do groupings based on similarities, right? And the last one we have reinforcement learning, right? Where the computer learns by try and error, right? Yes. And the steps to achieve machine learning, or how do we come up with a model for predictive analysis? We looked at collecting data, past data, a lot of data. Then when that is done, you have to do some pre-processing. We have to prepare the data, ensure that the data is clean. Sometimes whatever data that we get, sometimes they are messy. So we ensure that they are clean. When that is done, we do some exploratory data analysis. We try to explore the data to understand certain features, to know the similarities, to know the kind of feature, which feature is affecting another feature, right? So we come up with all this, yes, like intuition during the EDA state, right? So from there, we train the model. Sometimes when we say we are training a model, those who are not coming from the background of machine learning or just like AI, basically they would like to think of it like doing some heavy stuff, so right? But training a model is just a one line of code dot fit, all right? Then the model gets trained, all right? But before you get to that dot fit, then a lot of process has taken place, all right? So third, we train the model. When that is done, we test whatever that we've trained on new data, yes, like on seen data, to see how the performance look like. After that, if we're able to come up with good performance, then we put it into production. That's where deployment comes in place. All right, yes. Uh, Please, can you see my full screen? Give me a reaction if you can see the full screen. I'm presenting on, I'm using big screen, so I don't know those of you who are using maybe phone or laptop. I don't know if you are seeing the full screen, or yes, like I have to scroll. Right, yes. Okay, thank you. So let's look at one concept in that help us to achieve our probabilistic decision making, all right? And this is most important idea for today, all right? So basically, Bayes' theory tell us how should I update my beliefs, right? When I get new evidence, you get it. So sometimes you are going to start with a particular guess, right? You've not started with anything. If you want to know whether there's oil at this particular place, sometimes based on your what, yes, like experience, you could start with, oh, I can tell that this place there's oil here, right? So you come up with a certain number, certain probability, right? And at the end of the day, you use data, you do some assessment seismic data, and at the end of the day, your guess has to change, right? Your confidence has to change. So how do we do it? Yes, like update this confidence, all right? So that's where we are going to like look at the Bayes theory. That's going to be the most important thing for today. Please give me 1 minute. Okay. Sorry for that. I have to attend to something. Okay, so Bayes' theory. Today, before we go into any machine learning model for today, yes, like I would like you guys to get this one idea. All right. So yes, like engineers, yes, like engineers, we already have those what, yes, like intuitively, right? So basically, as I said, you start with a belief, then you get new data, you adjust it, right? So basically, that's the Bayes theory process, right? So you just put numbers on that process, you get it. So let's, yes, like assuming your geologist says there's 30% chance of yes like oil, all right? That's your starting belief, right? So you spend money on seismic survey, right? So that means that 30% becomes your prior or your starting belief, right? And when that is done, you spend some money on seismic survey, right? And the results look good, right? So now this type of seismic results shows up to like 90% of the time when there's yes like oil, all right? But yes, like also 20% of the time when there's not what, yes, like oil, right? So the question will be, given this what, yes, like evidence or given this new data, what should your new belief be? All right. So with this new belief that we are going to calculate, we are going to use Bayes' theory, all right? So as you can see from the formula, basically, I know those of us who have been taking statistic class, who have been going to statistic class, this is going to look familiar to you, right? So we have our yes, like IL to data. That's what we want, all right? Our new belief that we are looking for, all right? And when you come here, we have our data to oil, right? How likely this seismic results is if there's actual what? Yes, like oil, all right? So after the like results comes in, how is it going to yes like look like? Do you get it? If there's oil. And when that is done, when we get this, we multiply it by the P of oil. That's our starting belief. What we believe in, what, yes, like initially. That's 30%. You get it? Then you divide this by P of data. How common this seismic result is, yes, like overall, right? So at the end of the day, we are going to get our results to be 66 percent, right? Yes, that's like I don't want us to go into all the formulas and stuff. That's why I'm trying to make it in simple words. Yes, like English, so that no one gets confused, right? Yeah, so now that's our new belief that we've gotten. That's 66%. So that, yes, like initially we started with 30%, and that was guess because of we are what? Yes, like experienced in that field, right? So at the end of the day, we hired a seismic survey to come up with new results. So how confident, yes, like are we going to uh, put a measure to the new belief that we are going to get, right? And Bayes' theory, yes, like help us to come up with that. And at the end of the day, this theory powers most of them a model that we are going to look at, all right? So now that we are dealing with a single data point, right? So now what if you could do this, yes, like automatically with thousands of data points, right? Yes, like updating it continuously, right? So that's where machine learning models come to play. Do you get it? Okay. So there's one question that I would like us to look before we move on to the next thing. So based on this, based on what we've done, let's do this quick check. If your prior belief is 50%, and the seismic data strongly suggests oil, what happens to your updated belief? Right. So anyone with the answer could just put it in the chat for us to see. Is it yes, like is it going to be A stays at 50%? That means data doesn't matter. B goes up significantly. All right. So the strong evidence increase your confidence. And C goes to 100%. The data proves those. Oh yeah, yes. Let me see the chat if oh, I'm not seeing any answer in the chat.
Please, the question again.
Okay, so the question is if you can check from the screen. I'm reading from the screen. If your prior belief is 50%, right, and the seismic data strongly suggests it's like oil, what happens to your it's like updated belief? And the options are A stays at 50%, B goes up significantly, C goes to it's like 100%.
Hello. Hello.
Hi.
Okay. I think you need to walk us through the initial model that you wrote so that it can help us to decide the answer. The probability of the oil in the data equals to the probability of the oil in the data times the probability of the oil divided by the probability of the data. Can you just expand that a little bit to help us to make a better? Thank you.
Okay. Uh, okay, so do you mean I should go over the previous years, like explanation to that, or the actual calculation? So basically, this is just there was no, I didn't do any calculation. There was no calculation. It's just the probability of oil to data is equal to probability of data to oil times. This is the formula, right? So, and we try to I come up with a scenario to it, right? So what I was trying to let you understand is the whole the whole problem is, let's say, yes, like a geologist, right, come to a field, right, and says there's 30% of chance that we are going to get an, yes, like oil here. All right. So basically, that's the starting belief. There's no data to it. Yes, like he didn't use any data, nothing. It's just based on what, yes, like experience, based on what, yes, like that's like observation, right? That he has come up that we have 30% chances of getting, yes, like oil at this place. Right. And at the end of the day, you spend money on a seismic survey, right? We did a survey, actual survey, and get a data, right? And the data that comes in gives us a different result. Do you get it? So because we've gotten a new data, that means our result, that's, yes, like our first belief, yes, like, it's not going to be the same thing. Do you get it? By all means, the belief has to change. Do you get it? Or the confidence has to change. Do you get it? And that's what the Bayes theory helps us to get, the quantifying the belief that we are going to get when we get our new data. Do you get it? Yeah, so basically, this is the whole scenario. This is what the Bayes theory says, all right? And what I want you to, yes, like understand is when you start with first, what, yes, like belief, when there's new data, but by all means, your belief is not going to be the same thing. Assuming you started with 30% and there's new data or there's new survey from seismic data, the belief is going to definitely change. Like it's not going to be 30%, right? By all means, at the end of the day, you have to come up with a new belief, right? And how do you do it? How do you then, yes, like update this belief? And that's what the Bayes theory, yes, like help us to get, right? And now the question I was, yes, like I just put in, yes, some random question that if your prior belief is 50%, right? So assuming we are on a new site, right? An engineer comes in or a geologist comes in and says that based on this area or based on what I'm saying, there's 50% of chance that we are going to get an oil here. Right, yes. And at the end of the day, the seismic data suggests different and comes in with different and so now is the belief are going to stay at 50% or goes up or goes to yes like 100%. So basically that's what I'm asking, and I can see some answers in the chat. All right, that's great. That's great. Yes. So majority is saying that B, right? So basically the belief is going to goes up significantly, all right? And what I have to understand is yes, like evidence will do what? Yes, like increase the confidence, all right? But never reach, yes, like 100%. That's what you have to understand. Do you get it? And there's also there was yes like always some like remaining what yes like uncertainty, you get it, and that's okay. The whole point is making decisions with measured what yes like uncertainty rather than guessing. All right, so now we've been able to put a measure to our what yes like uncertainty based on the new data that we had, or based on the new data that gets yes like into it. All right. I hope the person that asked the question is okay.
Oh, very, very well understood. Go ahead.
All right. Thank you. Okay, so let's look at some of the models that we can use for risk analysis. Basically, we last 2 weeks we made mention of these models, right? Some of these models and how best we can use them, and we trained one of them, I think a couple of them, right? I have to cross-check and see, yes. We trained a couple of them, right? So b before that, we have to, like, for the sake of those who missed the last class, we have machine learning models, right? Before you can get a probabilistic decision, you have to first get a model that will come up with a probability distribution. Do you get it? So when you get this probability distribution from these models, then you use that probability distribution to make your yes like analysis, make your decisions. All right. So it's best we get to know some of these models. All right, yes. So first, random forest. Last week we look at it. When we say like random forest, we ask so many trees. The trees can be 500, yes, like a lot of them, right? And see how much they agree. Do you get it? So basically, as you can check from the code, this is the code for like random forest. So simple, easy, right? I told you the last time we have, yes, like sklearn, right? That's a library in Python that has most of these models, right? So you just yes like import them to use, right? So we have random forest. As you can see, this is a parameter, right? So we are saying that yes, like estimated is equal to 500. That means we are working with 500 trees. Please, are we good? So we can change after the first train. You maybe if the like model is not performing well, this is a parameter that you can change, right, to something else, and train again and see if the the guess is good. All right. Yes. So at the end of the day, I said we use dot fit to train the model, right? After we've gotten our data, S train and Y train, we just use dot fit and we are good to go. We've trained our data, and at the end of the day, what comes out is the probability distribution. So yes, like I keep on saying probability distribution, uh, like distribution is because whatever that we get from the model is probability distribution, and based on that, that's what we are going to use to make the decision. All right. So yes, like it will come up with a quantified what yes, like uncertainty. Then we use that quantified uncertainty to make our decision. We good. Yes, that's random forest, and same as Gaussian process. We import it from sklearn and do the same process. All right. Same as Bayesian neural network. This we didn't touch on this last week. This is new. This model is able to handle a lot of data as when you have a complex data, a huge data, uh, Bayesian neural network is the best. And when we say neural network, this has something to do with deep learning, right? I don't want to go into deep learning, but when we say deep learning try to mimic, yes, that's like our brain, right? Our neural, how our brain works. That's how deep learning works, right? And this Bayesian neural networks same works like our brain. Do you get it? Exactly. So if you have a lot of data to process, to calculate the patterns and trend, Bayesian neural network is one of the best model that you can leverage on to come up with your probabilistic probability distribution. Right. Yes. So after we've gotten our model to come up with the probability distribution, now we have to do some simulations, right? Monte Carlo simulation, and I know this Monte Carlo simulation is one of the most powerful tools in risk analysis. All right. And it just answers the question, what could happen? Do you get it? So previously or traditionally, what that's like engineers do is they basically guess this value. So this is what our what yes like that's like uncertainties, right? This is our parameters. Yeah. Yes, like uncertainties, right? So under normal circumstance or traditionally, the yes, like engineers will come up with one value, just a single value, or basically they guess this value, and at the end of the day, they just hope to see that they get something better, right? But Monte Carlo simulation help us to run yeah, that's like hundreds of run. Do you get it? And to see how the what yes like outcome will look like, or how our risks will look like. Do you get it? So instead of you uh calculating a single yes, that's like NPV, you just simulate yes that's like hundreds of future possibilities, right? And look at the risks. All right, so basically that's what Monte Carlo simulation help us to yes like achieve at the end of the day. And most of you think you know about it. So let's do some analysis here and see. All right. Okay. So now we have porosity, yes, like uncertainty. So this controls the it's like uncertainty of the reservoir quality, right? Yes. And we have the what? Yes, that's like oil price uh, volatility, right? So I've set these values to moderate, right, to low values to see how our runs will look like. So first, let's set this one to 3% as it is, and let's set this one to 15 as it is, and get a run and see how our risks would look like if we are to go with this, yes, like uncertainty. All right, yes. Uh, let's do 500 rounds. Okay. I hope we are following. All right. Okay, so with 500 rounds, this forget about this graph, right? So whatever this graph is telling us, that's what I've summarized it here. All right. Okay. So now we have P50, right? So the P50, this is the middle what? Yes, like outcome. And it tells us that half of this simulation are above uh, $442 million, right? And half of this simulation too can be below $442 million, right? So basically, that's what our P50 tell us, right? And the P50 value is $442 million. And I repeat, the P50 basically is the middle what? Yes, outcome, right? And it says that half of the simulations that we've done, yes, like half can be above this value. That's 452 million. And half of it is below this value. That's 442 million. Right. And now when we come to our P10 value is $227 million, right? And this is our downside case. I know uh, most of the petroleum engineers are conversant with this stuff, right? So that's the downside case, all right? So what it's trying to tell us is that 90% of the scenario is better than the $227 million. Right. And when we come to our P90, that's $698 million. This is our what's our pessimistic case, all right? And this tells us that only 10% of the what yes outcomes are better than the $698 million dollars. Right. And we have chance of loss is what 0.0%. So what that says is out of the 500 simulated futures, right, none are resulted in losing money. Do you get it? So basically, if we are to go with this yes like uncertainty, this value set, that means at the end of the day we are not going to lose any money. Do you get it? And what you have to understand is that doesn't mean that we don't have risks, or that doesn't mean zero risks, right? But what you have to understand is yes like it means under this what yes like uncertainty, loss is unlikely. Are we good? Yes. So now let's reset this simulator, right? And now try to, yes, like increase this, yeah, yes, like uncertainties and see what we are going to get at the end of the day. Please confirm for me if you guys are seeing my screen. Okay.
Yes.
All right, thank you. Let's increase this. Uh, this is okay. Okay, so now let's do 3,000 rounds and see what we are going to get at the end of the day. Wow. At the end of the day, like we are getting some losses, right? So that's how it works. That's how we use the simulator or Monte Carlo simulation to get our risk analysis, right? So at the end of the day, as I said, these values that we are changing, or these, yes, like uncertainties, most of the time, yes, like engineers guess these values, right? But now we are not guessing it. Do you get it? Why are we not like guessing these values? We are taking this value from our model, right? The probability distribution that we are going to get from these models. That's the values that we are using here, right? So at the end of the day, we are not guessing. We are just trying to get it from our models and just put it here. So with this one, it might quite faster, and also you can run, yes, like a lot of runs to see what the risks will look like to make a perfect decision. So as we can see from the graph, when we increase the, yes, like uncertainties, we are getting some scenarios as red lines, so we are getting losses, right? So basically, that's why we measure what, yes, like uncertainty to see how what, yes, like good, yeah, yes, like investment will look like. There's noise coming from someone's background. Yeah.
Okay, Bonsu, please, can you try if you can mute the person?
Okay, so let's continue. So let's take some real world case study to understand everything that we are trying to put across here. So let's assume a company has 8,000 kilometers of aging pipelines. Okay, let's continue. So a company has 8,000 kilometers of aging pipelines, right? And basically, this can't, they cannot what? Yes, like inspect them all, right? It's going to be too what? Yes, like expensive. All right. So they ask, can machine learning tells us what section are most likely to fail? All right. Yes. So now we have our problem, and the old method, yes, like engineers use some risk matrix and come up with high, medium, low, right? That's the old method. At the end of the day, that's what they get, and come up with something, all right? But based on what we've done, we are not going to go with the old methods, use some fixed risk matrix and come up with the answer, like whether it's medium, whether it's high or low, right? So we are going to use a machine learning model, right? So we train a random forest. We are going to train a random forest on 15 years of inspected records using the features, right? And the features are very what? Yes, like important as we said in our last previous. We have supervised learning, unsupervised learning, and reinforcement learning. So if you have all these features is that will decide which kind of machine learning approach to use, right? So we have the features. We decided to collect data, right? And this data consists of pipe age. We have wall thickness. We have soil type. We have coating conditions. We have pressure, yes, like history. We have past defects records. You get it. So we get this data and put it in inside like random forest or any model that we can come up on. And last week I gave you some clue that sometimes because machine learning is what, yes, like iterative process, you don't basically settle on the first model at once, right? Sometimes you come up with all these models and train them and see like which one is giving you best results as we did in our last class. All right, so we are using a random forest here, right, and at the end of the day, yes, like instead of the model to come up with medium risks or high risks, low risks, right? So then a model will come up with something like section 41B has 2.4% chances of developing a critical defect in the next 2 years, all right? So on and so forth. So basically, with the machine learning approach, we've been able to do what? Quantify this. Right. Yes. So with the what? Yes, adaptive what? Yes, like that's like element. So at the end of the day, since we are coming up with a model to tell us this defect or where there's yes like issue, we don't have to be doing this thing continuously. Like yes, like anytime there, yes, like engineers has to sit down and use the fixed Rex matrix and come up with something. No. So we are going to use what? Yes, like adaptive, yes, like Rex analysis. So as the data comes in, then we feed it to this model to come up with the defects, right? So as the data comes in, then we feed it to the model, right? So with this, we are going to realize that this is going to save money. So if we are to go to use this approach, we are going to save money at the end of the day, right? And the prediction is going to be quite good, right? Yes, like 99%. Why? Because the model is making prediction based on what? Yes, like experience, based on past data. Do you get it? So the model was, yes, like will come up with patterns and trend and be able to come up with good prediction. So at the end of the day, we get 91% prediction accuracy and 40% yes, like inspection cost savings, right? And surprise failures, like we are not going to get it because at the end of the day, it's what? Yes, adaptive. So as we get new data, then the model comes up with new what defects or something of that sort. So at the end of the day, we don't sit down and wait and there's going to be a failure, then we have to react to it. No. So it's more like proactive, right? Not reactive. Okay. So we have at the end of the day, the model is able to come up with the what feature what just like important. So sorry for that, last 2 weeks when you go through the a notebook, there was feature what yes like importance because I didn't touch that part because yes like, at the end of the day, yes, it wasn't part of the class, but I added it to then a notebook so that you can get more what yes like intuition from there. All right. So when we say feature what yes like importance, it tells us why the model is making some prediction, right? Or which one of the features is affecting the prediction or how has more what yes like influence on the prediction that we are getting. All right. So if you can see, we can. So this is very good to explain to what yes, like executives, your supervisors. At the end of the day, they want to see why the model is making such a prediction. What is happening? Right. You don't want to put them in black box. All right. So they have to know why this thing is happening. All right. So if you see from the results, we can see that the wall thickness is having much what yeah yes like influence on the prediction. All right, so we are getting 92%. That's the wall thickness. After that, we are get the yes like another feature that is yes like affecting the prediction or has much what yes like influence on the prediction is the pipe age. All right, the next one soil resistivity. The next one, coating condition. The next one, pressure. Yes, like history. So basically, that's how things work, and that's what happens in real world scenario. Yes, like out there. So what makes risk analysis yes like that's adaptive, right? So here's what separates good machine learning from great machine learning. Do you get it? Does it learn? Yes, like over time. All right. A static risk matrix is like a printed weather or forecast, right? So it's outdated by tomorrow. So an adaptive system updates what? Yes, like that's like every time that we get data. So as I said, when new data comes in, then the model is able to learn from the like new data and come up with the results, right? So at the end of the day, yes, like it's not going to be statics. Anytime that we get data, the model keeps on learning, yes, like updating, yes, like itself to adapt to the new data and come up with the best results. Get it? And there are three ways to do adaptive risk analysis. So do yes like adaptive ML, right? One, we have yes, like online learning. All right. So the model what yes updates each new data point. All right. So as we get new data, then it keeps on what yes like updating. All right. And the second one we have the Bayesian what yes like updating. And the last one has to do with reinforcement learning. we said this the last time, it learns by try and error, right? So when it sees new environment, it will just take some action. If this action doesn't yield good results, yes, like it will just go to a new action that will give him best results. So when this thing happens over time, the model adapts that, oh, if I take this action at this time, we are going to get this thing at the end of the day. If I take this action at this time, we are going to get this at the end of the day. All right. So that's reinforcement learning. And how the architecture works is the same thing. Red data comes in, right? So it's live data stream, right? So it's live data, it comes in, we detect, yeah, yes, like anomaly, some, like let's say that's a pre-processing stage, right? Then we use any model, whether you use, yes, like online Bayesian updating or like reinforcement at this stage, then you make a decision, like whatever engine that you are using, you come up with a right decision, right? And also sometimes we have what, yes, like human in the loop. Sometimes they like whatever the models come up with, or like whatever the decision that we get at the end of the day, we have human that are like reviewing and what, yes, like approving it. Do you get it? And sometimes it helps most of the time, because we all know that machine learning, yes, like AI is not 100% accurate. As I said, that was just few time ago. Machine learning or AI is not what, yes, 100% accurate. Do you get it? So we've not gotten there, and I don't know if we are going to ever get there. Right? Yes. So sometimes we need, yes, like human supervision in there to ensure that everything is running smooth. So what are some of the challenges that we have to pay attention to as we take on this decision, or as we use machine learning for probabilistic decision analysis and adaptive analysis? What are some of the challenges that we have to note them, right? So we are talking of what? Yes, like overconfidence, and sometimes it happens to just like all of us. Since most of us haven't trained a model before something, look at when you are using ChatGPT. Do you get it? Sometimes ChatGPT or any model that's whether Anthropic, ChatGPT, Grok, anyone, sometimes you ask them a question and they can come up with an answer. You yourself, you know that the answer that the model has given you is wrong, but the model is confident about it, right? Yes, like it can present it in a such a way that like you are going to believe it. Yes, like it's right. Why? Because sometimes it hasn't seen those data, right? Those data that are, yes, like it's coming in, or whatever that you are asking it's to do. Maybe it hasn't seen those kind of questions before, right? So sometimes it's not what just like able to come up with a right answer for you. But sometimes yes, like it will give you it as if it's right, but not right. Do you get it? And the second one has to do with bad data, garbage in, garbage out, right? So if you don't feed your model with the right data, you are not going to get the best out of it. All right. So most of the time, machine learning, the 90% of the job has to do with the data preparation, the data collection. 90%, almost 99% has to do with the data. Do you get it? You can have the best model, you can have the best parameters, and at the end of the day, if you are not having good data, you are not going to get good predictions. You are going to get bad predictions at the end of the day, right? So data, sometimes we don't have the good data. This is one of the challenges that may sometimes the like model can fail us, right? Bad data, because of bad data. And next one has to do with the world changes, right? You know that the world is not static. Day in, day out, new stuffs are coming, all right? So that's where what, yes, like adaptive risk analysis come in place, all right? So you have to ensure that you are making your model what, yes, like adaptive, that new changes whenever new changes comes in, the model, yes, like is able to take those, yes, like into consideration and make predictions. All right. So let me chip in this. Now, most of the models that we have, ChatGPT and stuff, now there's a battle about, yes, like AGI, and they are saying that a way to achieve AGI is continual learning, right? So when we say continual learning, so these models basically are trained on static data, right? So before them, so when the world changes, when there's new theory, when there's new what, yes, like information, these models don't have what, yes, like knowledge on them. They have to, those who train them have to get this data and train them again, right? So, but if you are doing continual learning, that means the like model keeps on learning, right? So whenever there's new data, like you don't have to take that's the model again and go and train it on new data. No, it keeps on learning by itself. Right. So another problem or another challenge is the world changes. And another way to solve this world changes is the adaptive risk analysis. And you have to take uh yes, like observation for that too. Right. And the next one, black box problem. Yes, so with this black box problem, sometimes we don't understand whatever that, yes, like is going on, right? So if you cannot, yes, like explain whatever that is going on, sometimes you have a risk of going like making certain things wrong or something of that sort. So that's why I made mention of feature what, yes, like importance, all right? So basically, when you look at here now, we have a fair idea on what is going on, why the like model is making such decisions, right? Who is accountable? It's not necessary. Cause of being wrong. It's not necessary, right? So basically, these are challenges that things that can go wrong that we have to pay attention to whenever we are trying to do machine learning for probabilistic decision analysis or something like this. Okay. So key takeaways, where to start, key takeaways and where to start. Last week I had some questions about this stuff, right? Yes. So yes, when key takeaways, yes, like always try to quantify, yes, like uncertainty. Do you get it? And that's what we did from the past lesson class from this class. That's what we've achieved at the end of the day, right? And second, use Bayes theory to update beliefs as new data, yes, arrives. And this Bayes theory is the basis of the models that we use. So we are good multi-color simulation. We've looked at it, all right, how to whatever results that you get from these models or whatever probability distribution that you get from this model, you have to use Monte Carlo to do some simulation to get the full range of what could happen. That's very important. Pick the right ML model. So with this picking of right ML model, you don't have to suggest one. I told you how we do it here. Minohot, not Minohot, yes, like Minohot, and wherever that, yes, like I've worked. We just select all this model. We analyze the problem and see what is there, what do we have, what kind of data that we have. Then we take all the model that can handle the problem that we have just like in hand and train them, right, and see which one is yes, like it's giving us a good result. And this one has to do with one line of code, for loop, then you are good to go. You train all of them and pick up the best one. And so you can be doing parameter tuning to just yes, like improve them, right? And build adaptive systems that's learn and yes, like improve over time. That's what we look. And ML drives human decision. All right. And your starter toolkit, you have to know Python, scikit-learn, all right, and NumPy, Matplotlib, and this is the data set that I gave it to you the last time, all right? Yes. So thank you for being here with me today too, and we this is where we will say goodbye to the first lesson and the second section. All right. So thank you. If there are any questions, I'm here to get them and answer put answers to them. Thank you.
Thank you so much, Abdul Malik, for your insightful presentation. I think we learned a lot so far from risk analysis and the power of adaptation in this current world. You need to also open yourself to new opportunities. We also learned that the data quality is very, very essential when it comes to the input you give to the what do they call it, machine learning, to be able to produce also quality output. So please, at this point, if there's any questions, kindly send them to the chat box so that we look at them. And also suggestions are also welcome. I think Malik, there are some questions for you. One is saying that one challenge for young professionals is the selection of the right distribution of use. Could you please touch on that a bit?
Okay, so that's great, and that's what basically we answered here in the. So basically, the model will come up. These models, the machine learning models will give you the distribution, right? So when that happens, you have to use Monte Carlo if you want to see the wide range of what is going to happen. You use this Monte Carlo simulation for whatever distribution, probability distribution that you are getting from these models. You use this Monte Carlo simulation to come up to see how the rigs will look like. All right. So yes, like importantly, that's why we are treating this topic, how we can use machine learning for probability risk analysis. And so the machine learning previously, what yes, like engineers do is they guess these stuffs, right? They guess this, yes, like inputs, right? So now machine learning is giving us this probability distribution. It's giving us this, yes, like input, right? So we don't have to be guessing them. Do you get it? So that will take time. That will waste our time. We don't have to guess them. We just use these models to make to get our probability distribution and now simulate it to see how the results will look like at the end of the day. If we are to go with the prediction from the model, what's how it would look like. So simple answers to your question is you use the models. This model will give you the distribution, and now use Monte Carlo to simulate this distribution, and at the end of the day, you get a fair idea yes, like at the end of the day. So your hustle at the end of the day is being solved by the machine learning model, and that's why we are looking at it today.
Thank you so much for the um for your input, Mr. Malik. If you have any other suggestions or inputs, kindly send them or raise up your hand to bring them out. So, Malik, I have one over here saying that as we automate probabilistic decisions, how do we audit our models to ensure that we aren't codifying historical human biases into our new digital system? I don't know if you got that. Let me take it again. As we automate probabilistic decisions, how do we audit our models to ensure we aren't codifying historical human biases into our new digital systems?
Okay, all right. That's a great question. So first, uh, at the end of my last presentation, I made mention of yes, like human in the loop, right? That's first answer to the to this question because we know that this is sometimes this stuff yes like is going to happen, right? So sometimes you need what yes like human in the loop to sometimes validate these stuffs. And also, what we've done here, secondly, what we did here is just on our yes, like machine, right? So
Gotcha.
with full machine learning pipeline, we have
Give me a moment.
yes, that's like monitoring system, right? So when we deploy these models to do stuff for us. We have a yes like monitoring system that we monitor them. Do you get it? And there's a percentage. Do you get it? So when you see this, maybe this is more what yes like advanced and yes like industry standard. But what I want you to yes like understand is in real world what we do here. We have monitoring systems to monitor this yes like more models when we deploy them. Do you get it? So anytime that there's a change, do you get it? Let's say a data change or there's a change, that's the performance drops. Do you get it from the monitoring system? Do you get it? So yes, like as soon as we notice a drop from the performance, then we quickly check the kind of data that is coming inside. All right. So first, when we deploy these systems, we have a monitoring systems to check the performance day in, day out. Anytime that there's data inside, we are keeping track of the performance of the model, right? So anytime that yes, there's a decrease, we notice that and quickly trace it to the data, what is coming in yes, like is it good so that we verify them, right? So that's basically second way that we ensure that we are not doing the right thing to solve what the question that you answer. That's how sometimes we used to solve this problem in the what yes like industry. I don't know if I'm clear here.
Very, very, very. I appreciate the insight, Mr. Malik. I think at the end of it, we are trying to say that having this knowledge in machine learning as professionals, okay, let me use the word young professionals in this case, is very important in addition to the petroleum industry knowledge that we've acquired from school. And we really appreciate this opportunity from the guidance and outreach team. And also really appreciate Mr. Atuedu for the input.
Exactly.
If there's
Let me chip in this one. You
all
made
right,
mention of something, and I want to chip in this one.
all right.
The people that are making good use of machine learning, or those basically, from my point of view, the people that I see machine learning to be helpful to them, right, is those who are what, yes, industry. Let's say petroleum, what, yes, like engineers, yes, like electrical, yes, like engineers. If these people learn machine learning or get the idea of machine learning, they are the ones that make good use of them. Do you get it? But let's say I'm coming from computer what, yes, like engineering field, or let's say I'm coming from computer science field, right? I'm just like learning the technology. I've not been into the space to do what, yes, apply whatever that I'm learning or something of that sort, right? So those who are in there, if they learn this, they have some ideas or they know how machine learning works, they able to know, yes, like machine learning, they are, yes, that's what, yes, like able to solve problem quickly, like be able to make good use of these models than those that are just learning the thing without any domain, without coming from any domain or something of that sort, right? So basically, like what I'm saying is, those in the what, in a specialized what, yes, like industry, like petroleum what, yes, like engineers, you are the ones that if you're able to learn machine learning, if you're able to get machine learning, the understanding everything around it, you're able to make good use of them to get, at the end of the day, to get productivity and help you excel in your space. Yes.
Really appreciate that adage. I think myself also in the maritime industry, I also have to take advantage of it whilst it is the day is still bright, the night is still young. So I want to really appreciate Mr. Atuedu again for his contributions. And I want to acknowledge the section chair, Prof. Amorin, also for joining us. Thank you so much for your time. Are there any suggestions and inputs we would like more clarification on? Are we on the same page at this point? I want to know if we can ask some questions. Mr. Malik, do you have some key takeaways? I think we should go back to the slide for the things we named as the key takeaways so that we'll go over them before we close today. So at the end of these two sessions, we are trying to say that if you are to take something away, there are two or some key items that you have to add in addition to the knowledge you already have. Yes, I think. And for us who also want to start this journey on machine learning, it's very important that we take note of these few things. I think the first one, it says always quantify uncertainty, say 70% chance, not just likely. I think these are some key takeaways we can have. We should use the bias theorem to update beliefs as new data arrives. And also we are saying that the Monte Carlo simulation shows you the full range of what could happen. And also saying that you should pick the right machine learning model, random forest, GP, or RNN for your data. We are also saying that we should build adaptive systems that learn and improve over time. And also the machine learning advices that human decide. We should keep the engineer in the loop. I think the last one is very, very important in this our space, so that we don't leave everything for AI to do or machine learning to do. Thank you so much for this presentation. We want to remind you that there is still opportunity for you to register for GH Buys until next week. And we want to also keep ourselves updated with future webinars that will be coming up. Is there any other contribution we would like to take in before we take any other contribution? So on that note, we'd like to say a big thank you to the SE Career Guide and Outreach Committee and for giving us this opportunity to learn outside of our classroom and delve into the world of machine learning and able to make better decisions for ourselves and for our companies, industries, and the world at large. Want to thank you as we have for those of us who have also joined. Want to take this information, let us put it into practice, and let us develop ourselves to be able to help ourselves and also our industry. Thank you all once again for this, for your time and for this session. I think until our next meeting, this is a bye-bye. Thank you also, Mr. Samuel J. and Engineer Daniel Opong for joining us. Thank you once again, Mr. Richard, Prof. Richard Amorin for honoring this call. And thank you everyone else. I see Janet. Thank you all so much. Let's have a few reactions as we take our leave. Kofu and Seattle, thank you for joining us. Kelvin Seram, thank you for joining us. Osai Bonsu, thank you also for joining us today. Looking forward to our next session.